Hi everyone, today I'm going to show you how to control an AC fan using an Arduino. In my example, I'm going to be using an Arduino Nano and a Robot Dylan AC light dimmer module. Now, don't get confused by this name because really it's just a 0-point cross detection module. By that I mean it puts out an interrupter signal at every 0-point cross of a sine wave, in our case an AC sine wave. Just to iterate that, they do also note that it can be used on fans and pumps, air cleaners, etc. So, yep, we're using a Robot Dylan AC light dimmer, but it's a 0-point cross detection module. As I said, we're using an Arduino Nano as well. The reason we're using a Nano is because really this code should be running independent of any other tasks. So really it should be running on a slave MCU. In general, I connect my slave MCU to another Arduino, let's say Nano, another Nano or a Uno or a Mega or whatever, and I'll connect them via I2C. In this example, I've just set the I2C address as 9. This is really not related to the fan speed control tutorial itself, but it is quite important that you use I2C to send the fan speeds if you are going to run it on a slave, because it has to run very quickly. This entire code, that is. Before I explain this code a bit further, you may not be familiar with sine waves, so perhaps I should explain it a bit first. Here we can see a standard sine wave. In this example it's at 50 Hz. A full sine wave is comprised of two half sine waves, a positive and a negative. And of a full sine wave you have 3 zero-cross points, as you can see. The time of 50 Hz of a full sine wave is 20 milliseconds. Obviously we have 50 full sine waves at 50 Hz, and we have measuring that against a full second. So we're really interested in the half sine waves, of which of course they'd be 10 milliseconds at 50 Hz. At 60 Hz I believe it's about 83.3, so not 83.3, if we're at 20 here, a half sine wave would be 8.3 milliseconds. Now that I've explained the sine wave, I should note the two different methods that you can use to control a fan. Robot Dylan provide some code. Of course, some connections there, but I know why. It's because their horrible website is overlapping. But they do provide a tutorial, and in their tutorial it does it's horrible. You can find it somewhere on there. There we go. Nonetheless, their tutorial uses something called pulse skip modulation. Now what that means is their code, to be specific, actually skips out a half sine wave, not a full sine wave. So this example is not completely accurate, but the principle is the same. Pulse skip modulation, you essentially turn off the AC and exclude a full or half sine wave every X amount of 0 points. That's up to you how you'd set that. The problem with that is you have very poor control. It's not a uniform sine wave. For instance, you could be skipping one full sine wave every 3 sine waves, and it's not symmetrical. You wouldn't be able to run a fan at many speeds, and if you're trying to control something like a light, you'd find it would flicker quite a lot. It's got a lot of harmonic noise as well. Now, the other way you can do it is cut up an AC sine wave. By that, I mean after you've received a 0-point cross interrupt, you would turn off the AC for a given period and then turn it back on, to which it would slope back up. It wouldn't rise up vertically, rather it slopes, and then it continues its sine wave. And the same is repeated for the both positive and the negative, so both halves of a full sine wave. Now, this is a much better method because it's completely uniform and symmetrical, and it has no harmonic noise, and you can get much greater accuracy on speed control of a fan. I will show you later on an example me using an oscilloscope to prove this, but this is the principle we're going to be using. We're going to be cutting up the sine wave every interrupter signal. So let's go back to the code. Sorry, got a bit of a cold here. So I'll explain our main variables here as we go through the code. So we'll start with the setup. Now, in general, I wouldn't use the serial. This is just for debugging. So in this tutorial, I don't have to set up a slave connected via I2C. I can just input some values via the serial monitor. The reason I wouldn't use serial is, again, we have to have this code running very fast. Really, if you're at 60 Hz, this code needs to loop within 83 microseconds, or at 60 Hz, yes, 83 microseconds, or at 50 Hz, 100 microseconds. Now, the reason for that is because of a half sine wave at 50 Hz, that would be 10,000 microseconds. And if we divide that by 100 speeds, would then be that there's a million microseconds in a second. Therefore, there's 10,000 microseconds per 1% fan speed. And of that, we need to accurately get to that point and turn off the fan so that it's nice and uniform. So did I say that correctly? Yes, so this is 10,000 microseconds long. Divide that by 100. Therefore, that would be 100 microseconds per 1% fan speed. So this code needs to loop within 100 microseconds. And this code currently loops at about 4 microseconds. The reason for that is I'm using port manipulation and direct registry manipulation. We're not using digital write high and low because that has quite a lot of subroutines to go through before it sets the pin high or low, and it takes too long. So here, it's not really necessary in the setup, is it? But here I use the direct registry manipulation to set pins 3 and 4 high. You start from the right, so that's pin 0, pin 1, pin 2, there's pin 3, and there's pin 4. I'll set them both high. We've set the ITC to begin, so we can get data from a master. Here I've set the address to 9, and I set a function to an interrupt function on the ITC to call the function directly here. We also have an interrupter attached to pin 2 from the 0-point cross module. As I said earlier, the 0-point cross module outputs an interrupter signal at every 0 cross. So we've attached an interrupt to digital pin 2. We've attached this function, 0 cross event, and we've attached it on the rising of our interrupter signal because we want to react straight away. And of that, the signal, the interrupt would, if you did it whilst it was high, that interrupt signal would be of given too long of a given period, and therefore would miss our chance to react in time. And we don't want to have to do it on the low side, so we do it on the rising. Probably explained that too much. So yeah, we've attached an interrupt to digital into for a 0-point cross module, and we've attached an interrupt for our I2C event to set fan speeds from a master. Just for debugging, I have a serial function that wouldn't be used generally. Again, serial's too slow, so we'd be setting it via I2C. But yeah, we have this function just for this tutorial, and the only other function that would be in the loop, or should I say the only function that would normally be in the loop, is this cutoff event that's obviously running every loop. Now I'll explain the functions in more detail. I suppose I'll start with the I2C receive event. With a I2C receive event, you need to define a parameter, or should I say an argument, or an attribute, and this is the amount of data that we're receiving. So here we're going to be receiving two values. You can't put it as a constant ref, you have to have this constant in. The function's hard coded, I tried. But here we're going to be receiving two values from our I2C. One is a switch case, by that I mean a char. We can see an example here. And the other is a value. In our case, it's the fan speed. Here I'll show you some examples. So switch case Z, and the value is a range from 0 to 100. Fan 1 speed in percent. An example being Z50. We set the fan 1 to 50%, and we have fan 2, same principle here, but the switch case is X. Well, I've also defined the pins there for you as well. So once we've received our two values, we would then say, is it switch case Z or X? Let's say it's Z. If the value is 0, therefore a fan speed of 0, we obviously want to turn off the fan. So we use our port manipulation and write pin 3 line. Pin 3 being the BDM signal of the 0-point cross module. Let's get a little example, which in this case would be pin 13. That controls the triatic switch to turn on and off the AC. So if you get a fan speed of 0, we turn off the AC, therefore the fan's off. And I'll explain this a bit more later on, but we set the fan timing to 0 because we don't want to chop up the AC sine wave. And we also don't want the function in the cutoff event to run either, so we've set that to the false as well. If it's 100%, we obviously then want the fan to be constantly on. We're not cutting up the sine wave at all, so we'll just set port 3 high, therefore turning on the triatic switch constantly and the AC constantly, so the fan will be at 100% fan speed. And again, we don't want to cut up the fan wave, so we set that to 0. Else, if it's not 0 or 100, we do want to start cutting up the fan at the AC sine wave. So I'll explain this calculation a bit. We need to invert the user's fan speed. So if they sent a fan speed of 75%, we want to invert that to 25. So we've got our fan speed percent of 75, for example, minus 100 minus 75 would equal 25. So 25 times half wave duration. Now that's the duration in microseconds, but I'll explain that a bit later on. That's 100th of the half wave duration in microseconds. So if that was 10,000 microseconds, that would therefore be 100. So 25 times 100 would equal 2,500 microseconds. So they sent a speed of 75%. They want 75% fan speed. 100 minus the 75 would equal 25. 25 times 100 for 50 Hertz would equal 2,500. Therefore, we've got our interrupt. We're waiting 2,500 microseconds, B, being a quarter of a half sine wave, and then we're turning the AC back on. Therefore, we've effectively taken a quarter of the AC power of the fan. Therefore, we're achieving 75% fan speed. And exactly the same principle for fan 2, just a different switch case. So again, I'll explain that variable a bit more later on, but we're inverting the user's fan speed and then timesing it by 100th of the half-wave duration in microseconds. Now you're probably thinking, well, how do we know if it's 50 or 60 Hz? In this zero cross event that's running each time we get a interrupter signal from the 0-point cross module, we're going to, for the first two sine waves, and only those two, on the boot of the device, we're going to work out if the AC is 50 or 60 Hz. Now we do that by, on our first 0-point cross event, if this is set to 0, which it is by default, we're going to set the current time in microseconds. Then, on the next interrupt, that being, so we've got this interrupt, now we're getting this interrupt. We're now going to measure how long this half sine wave was. So we set the current micros on the first interrupt. On the second interrupt, we're going to take the current micros minus the last micros. Therefore, we've got the period. Now, your your sine wave might not be exactly 60 or 50 Hertz. It might be 59.99 or whatever, 58 or whatever it is, or it might be 60.1 or a bit higher. So we're actually going to measure from 59 to 61 for 60 Hertz and 49 to 51 for 50 Hertz. If our half-wave measurement falls between those two values, as I said, we're going to set that to 100th of our period, so that would have been 83,000 for 60 Hz or 10,000 for 50 Hz. We're setting the value there, so therefore in this bit here, as explained earlier on, we're using that to calculate the cutoff period. So we've now worked out on the first two interrupts if it's 50 or 60 Hz, and just for debugging, we'll print out what option it chose. Once that's set, on all other interrupts, we're then going to say, is the fan timing not equaling 0? Or effectively, is the fan timing not 0? Sorry, I was trying to read the code there. Is the fan timing not 0? As I said, that would be set to 0 if our fan speed was 0 or 100, because we don't want to chop it up. But let's say we set our fan speed to 75%. Therefore, we've at 50 Hz. Therefore, we've got a fan 2 timing of 2500. So we're down here now. We've got our interrupt. This doesn't equal 0. We now want to work out when we want to turn the AC back on, because we're about to turn it off. We take our 2500 and add it onto the current time in microseconds. That's going to be when we're going to turn the fan back on. We then immediately turn the AC off, again using port manipulation, and we're going to set an event so we can know if we need to turn the AC back on. Again, up here, we set this to false if we didn't want to mess with it. So here, we've set it to true. So now down here, you can see, are we ready? Can we start finishing the fan cutoff? Yes, that's true. And is the current time in micros greater than the time we set here? In our example, that was 2,500 microseconds in the future. When that eventually is true, hence why we need this to loop very, very, very fast, because we want to get this as quick as possible, match this time as quick as possible. Once this is true, we're then going to turn the AC back on and set this to false. So this won't run again until this is set again in our interrupt. And that's just going to repeat forever. And that effectively is doing this. We're turning off the AC, awaiting our 2500 microseconds, then turning it back on and letting the AC continue its sine wave. So we've chopped it up, and then on the other minus side of the sine wave, we're doing the same, and that just repeats until the users change their fan speed, and then obviously the timing will change for the given speed. And that's why we need this to run really, really quickly. If I was to show you how quickly this loops, I'd expect it to be 4 microseconds, and to that extent we could actually have about 500 unique fan speeds, potentially even 1,000, but I'd account for the first loop and then setting in the second loop, because again we need 2 interrupts, so really 500 different fan speeds. But let's have a look how quickly it loops. So that's what we just saw there, was this working out the duration. In England, so it's 50 Hertz. But let's just upload this code so we can start printing out some loop times. Four and 8, more than acceptable. More than acceptable. We've got, in worst case scenario, 100 microseconds window, or should I say worst case scenario, 83 microseconds at 60 Hertz, or 100 microseconds at 50 Hertz. So therefore, we don't need to print all that, it's just slowing down our code. So obviously we'll turn that off. We don't even need to set that either. And as I said, we're using this just for the example, but I'll just load this back up, just so we're not messing up our window. And let's open this back up and clear that. So it's set our duration, half-wave duration, or should we say 100th of a half-wave duration. Let's clear that. And we got our switch cases here. The same switch cases can be used with the serial debug. I've got a fan right next to me, so. Alright, so we've got our 0-point cross module here. We've got our nano, and we've got our code there. And here we're just measuring the input, so you can see it's a nice standard waveform. This is just a little mini oscilloscope, just because I'm sat in my chair. Nonetheless, oh, slipped the pins off. It's rather hard to hold 2 with one hand. It's like holding a pair of chopsticks. Nonetheless, there's our waveform. So we've got a fan down there, 150 mil. So let's turn it to 50% fan speed, and we can look at the waveform. Well, we're set at 40%. It's a bit late. So, gotta be careful, there's live AC right by my hand. Where's the serial monitor hiding? It's down there somewhere. So if we just restart the Uno, just so we can see it set some stuff up. So yeah, we've got a duration of 100, so we're at 50 Hertz. And it's Z for fan 1. So let's send that over. Trust a bit of my camera to be right in the way. It's a bit dark in there. Anyway, I said 40%, didn't I? But just to be even more funny, we'll do 30%. No, I said 40. I don't know why I'm being so fussy. Here it's starting up. Let's get my probes out. Just get them around the right way would help.
There we go. As I said, more like a shark fin than a sawtooth. Yep. Nice and happy. Let's increase the speed a bit. We're now at 50% fan speed. Cool. Turn that off just so I don't electrocute myself. Cool. And that is essentially how you control an AC fan with an Arduino. Thanks for watching.